Today we are wrapping up chapter 20.1 and talking about Lenz's law. First, let's review what we talked about last time and calculating magnetic flux and induced EMF. So here we have a coil with a wire that's wound around a 2 meter squared hollow tube 35 times. A uniform magnetic field is applied parallel to the normal. If the field changes from 0 Tesla to 0.55 Tesla in 0.85 seconds, what's the induced EMF in the coil? So we're changing the magnetic field strength, so we'll pick our equation for induced EMF that deals with changing magnetic field strength. And then plug in our variables. So we know what N is, 35. We know our area is 2. We know our time is 0.85 seconds. We know our change in flux. Our change in magnetic field is 0.55 Tesla. So then our induced EMF, I don't have a fancy E here, is negative 35 times 2 times 1 times 0.55 divided by 0.85, which is then negative 45.3 volts. Today we are wrapping up this section, as I mentioned, by talking about how we can apply Lenz's law and look at how that affects the direction of induced current. So Lenz's law states that the current induced in a circuit due to a change or motion in a magnetic field is directed so as to oppose the change in magnetic flux and to exert a force opposing the motion. I think the simplest way to kind of think about this is another way to say Lenz's law is nature hates change. So if we have a loop of wire, like over here, and we have this magnet coming at it with the magnetic field lines pointing to the right, nature hates change. So it's going to create a magnetic field that has magnetic field lines pointing to the left to get rid of these magnetic field lines pointing to the right. So then, if the magnetic fields point to the right, we can use the right-hand rule that we learned last chapter about a current-carrying wire and wrap our hand around the wire so that our fingers point to the left. And in that case, we get the current to go in this direction upward or around this as it's oriented. Similarly here, we have a magnet that has our magnetic field lines pointing to the right, but it is moving away from our loop of wire. So Lenz's law, nature hates change. It's losing magnetic field lines to the right. So that means that our loop of wire is going to have an induced current that causes a magnetic field pointing to the right to make up for these lost magnetic field lines. So we can use that same right-hand rule, wrapping your hand around the wire, and you get the current going around this way. Last example here, we have the magnetic field lines pointing to the left. Our magnet is moving to the right. That means that this loop is having magnetic field lines going it to the left. Nature hates change, so it's going to create magnetic field lines going to the right. And then we'll wrap our hand around the wire using the right-hand rule, and we get this current going down and around like that. Another way, or the way that Lenz's law is denoted in an equation, is it's just the minus sign in Faraday's equation. So Faraday's law, we learned, has that negative sign in it, and the negative sign is technically called Lenz's law. And so it tells us that the direction of the induced EMF is always going to oppose a change in the magnetic flux. So that wraps up 20.1. Please contact me if you have any questions.